know it's probably tiring to have to do this today. Oh, whoops. Um, Especially since this is the last time we'll be able to do this since break, and I'm sure everyone's burned out because I'm sure everyone's been having a busy week. But I still appreciate you guys for coming. So as you probably saw, today's lecture is going to be on etching and metal deposition. So before we really get into it, I just have like a couple things to say, or not really a couple, just really one, which is next week, the day after we get back from break, we're gonna have another Arduino project meeting. This one's gonna be less lecture as it's been previously, and it's gonna be more focused on giving you an opportunity to hopefully meet with your teammates and work on your budget, because we are gonna try to get budgets in before Christmas break so that we can put in the order for all the parts, and then hopefully at the beginning of the spring semester we'll have all of the parts that we need and we can get them out to you guys as soon as possible. So if you have next Monday available, we would really appreciate it if you could try to show up if you are interested in participating in the Arduino project. So lecture 5, we're going to be covering etching and metal deposition, particularly wet etching and dry etching and the differences, and then chemical vapor deposition and physical vapor deposition. So etching, generally speaking, if you remember from the general processing overview presentation that we gave a few weeks back, wet etching is, or etching in general, is the process of removing either chemically or physically the oxide layer from our substrate. So you, at this point in the process, you will have oxidized obviously onto your substrate, and then you will have done your first layer of photoresist. So at this point in this of the process, you have a oxide covered substrate with photoresist on it in the pattern that you want. And so etching is basically removing the excess oxide that you don't necessarily need in order to have the oxide layer mimic the pattern that you have in your photoresist. So wet etching performs that by chemical means. So it's a form of chemical etching which involves the exposed. It's chemical etching where the exposed grown oxide layer is removed. So whatever isn't covered by photoresist is going to be removed, and it's done by basically just dunking your wafer in a chemical bath for a certain amount of time. It's an isotropic process, meaning that it affects the area surrounding it equally in all directions. This leads to undercutting, which is demonstrated here. This is technically, I got this picture from online. This is technically the photoresist. It shouldn't say mask. Um, but you can see how the uh, the oxide layer is actually etched underneath where the photoresist is, and this is called undercutting. And while there's not anything directly bad about it, it just makes your process a little bit more imprecise, because when you're taking into account the time that you need to etch for, if if you want to etch truly all the way down to pure silicon, you have to make sure that you have your oxide layer is the proper thickness to where it can etch down to the pure silicon without going too far underneath in undercutting underneath your photoresist. And so this is just kind of a diagram to show what undercutting really is. So you're starting over here. This is a really zoomed in picture of our devices. So let's say that this little circle is where your photoresist actually lies, and then completely surrounding is is the oxide layer. So the photoresist is on top of the oxide, and ideally, when you etch, you would get the oxide layer perfectly underneath the photoresist, and it would be the exact same. The photoresist circle and the etched oxide circle would ideally be the same, and now surrounding it should be bare silicon. However, with an undercut, what you actually get is that the etched oxide layer is underneath the outer edges of the photoresist. So you have a smaller oxide layer than you were truly intending for. And so that can just be a little bit more problematic in terms of alignment and things like that. Um, but some more specifics with wet etching. The etching that you use depends on what substrate you are etching. But for silicon dioxide, we use what's called BOE, which is buffered oxide etch, and it's a dilute solution of hydrofluoric acid buffered with ammonium fluoride. And so the benefit of this is number one, the added ammonium fluoride. Was, while hydrofluoric acid is a very volatile acid, the addition of ammonium fluoride um, causes it to be much more controlled. Um, I think usually the one that we use in the lab is a 7-to-1 ratio of water and ammonium fluoride to hydrofluoric acid. So relatively speaking, it is much much lower concentration hydrofluoric acid than pure hydrofluoric acid. Um, but it's still very, very dangerous. But the benefit of doing this is that you get more controlled etching, and it promotes to make sure that it truly acts isotropically, meaning attacking equally in all directions. Um, and the other benefit of using hydrofluoric acid in particular is it only reacts with the SiO2 and it doesn't react with bare silicon, or it doesn't react. The process with SiO2 is much more favorable than Si, um, which makes which means that it will basically always attack the oxide layer, and your pure substrate will be perfectly fine. So let's say you mess up during a process, um, you mess up the I don't know, maybe you mess up development somehow. You can just etch all the way down to pure silicon, and you can reoxidize your wafer. There will be no disadvantages to doing that, and so that mostly covers everything on this slide. And now we can move on to dry etching. Dry etching it can occur through physical or chemical means by either kinetic energy of gaseous particles or the chemical reactions between the substrate and the gaseous components. You have two common types. You have sputter etching and reactive ion etching, or RAE. Sputter etching is commonly known as ion milling, where essentially they have a very hard flow of inert gas that's accelerated onto the substrate, and it physically is ionizing atoms and molecules within the substrate and knocking them away, and it creates a planar surface. And so um, there's that, and then there's also reactive ion etching, which is a combination of physical and chemical erosion, where a chemical radial is formed and accelerated towards a substrate. Essentially, what this means is that a plasma is used and projected over the substrate, and it will react. It will chemically react with the substrate, and also you have the accelerated particles, which will then vaporize the substrate little by little. And so both of these processes are much more time intensive than wet etching, um, but they're also much more precise. Uh, they're much more precise and you have a lot more control over them. And I'll get more into the differences later. So dry etching, compared to wet etching, it's anisotropic, which means that it's good for creating vertical oxide walls as demonstrated down here. You have no undercutting, um, because as you apply um, the plasma, or if you're ion milling, you're purely just removing the SiO2 layer, and you're not even touching the photoresist. The main drawback of dry etching is that it may generate bubbles, Since you're producing plasma, it's going to be pretty hot, and you may actually evaporate excess solvent that you've used or any water, and will evaporate out, and it will generate bubbles inside of the photoresist, which will make you need to go back and rework steps. And as I mentioned before, there's generally a slower etch rate just due to how the process works. Um, and one benefit of the process itself is that less PPE is required when working with it compared to wet etching. Because with wet etching, since you're working with hydrofluoric acid, despite it being extremely diluted, hydrofluoric acid is very, very, very dangerous. As it doesn't burn you, it works its way into your bloodstream, reacts with the calcium in your bones, and then if enough calcium has reacted with the fluorine and the hydrofluoric acid, it will give you a heart attack when it blocks up your arteries. So there is some risk working with hydrofluoric acid, even in dilute amounts. But obviously, it's just an extra precaution you need to take. With dry etching, you don't need to take that risk because it's usually contained in some sort of machinery, and you're not ever truly exposed to the plasma or anything like that. This particularly gets into RIE, which is the I forget the acronym, uh, reactive ion etching. Um, so it typically etches gases. It typically uses gases for etching SiO2 that are either fluorinated or chlorinated. I didn't mention the chlorine on here, but they're usually hydrocarbons of some sort. And most commonly, in my research, I found that CF4 is pretty common. Um, and basically, the mechanism by which they actually etch is that free F ions or free F atoms are formed by impacts with electrons, and then the fluorine atoms will then react with the silicon dioxide, creating SiF4 and oxygen. And SiF4 is extremely volatile, which will means that it will vaporize at a low temperature, which then therefore etches away the silicon dioxide. So this is just a quick chart between wet and dry etching. So on the left in the blue you have dry etching. On the left you have wet etching. So we went over this. Dry etching is done at a plasma phase. Wet etching is done in liquid, gaseous chemicals versus liquid chemicals. Um, Dry etching is much safer than wet etching. Um, I briefly mentioned the risks of using wet etching and hydrofluoric acid. You're usually working with a lot more dangerous chemicals. It usually requires two people to work on it at once, just because as long as someone has been exposed to hydrofluoric acid, even if it's just on PPE, you are not allowed to touch anything else in the lab. Once when your hands go inside of the fume hood that you're working with the hydrofluoric acid on, you are not allowed to touch anything else in the lab because hydrofluoric acid is a clear, odorless liquid, and it's indistinguishable from water if it's on a surface. So if you see a drop of any clear liquid in the lab, once when someone puts their hands in the fume hood, you have to assume that it's hydrofluoric acid. So it can be a lot more of a hassle working with wet etching than dry etching, particularly for that reason. As I mentioned before, dry etching is much more precise. You can get nanometer accuracy with dry etching. With wet etching, you're usually looking on a micron scale. Uh, Uses few chemicals. With dry etching, you have to most likely use a few chemicals while you're working with wet etching. Um, the main drawback with dry etching as compared to wet etching is that it's expensive because, as I mentioned, you do have to use specialized equipment and equipment that contains all of this. Wet etching isn't very expensive because you only need a chemical bath. The other thing is that it's not on this chart, but you can also do mass wet etching. You It's not recommended to try mass dry etching since it's just a chemical bath. As long as you're taking the wafers in and out at a consistent time, you can do mass wet etching. And obviously, as long as you're okay with putting in the resources to mass wet etch. So now we're going to move on to metal deposition. So metal deposition is the method of uh, ionizing or evaporating metals and applying them to your substrate to use as gates. Um, so at this point, you would have. So let's say that we're done with the etching now. You would do a second layer of photolithography, and you would apply a new layer of photoresist onto your substrate. It would give new imaging, and then essentially what would happen from there is now you would have this new photoresist pattern on top of your on top of your substrate, on top of your what is left of your oxide layer. And so what you would do here instead of instead of well, I mean, you'd still develop, but there would be much less developed off in the developing process. And so basically what this does is that when you apply a metal gas or metal vapor, it will stick to the what's on the photoresist. It will coat the entire wafer, and then you can um, put a put your wafer in a sonic bath, and it will vibrate at a very high frequency, and it will lift off the photoresist along with that metal that's been deposited onto it, and that will give you your gates. So we're going to particularly talk about the methodization of the actual application of the metal. So as you can see here, the thin film deposition is depositing a layer of material onto the wafer. It can be used for insulation and also metal applications. There are two overall methods of deposition. There's chemical and physical, and we'll go into both of those. We'll particularly spend more time on physical than chemical, just because that's more of what applies to SCRO, generally speaking. So, oh, hang on, sorry, I clicked out of that. So chemical vapor deposition, also known as CVD, is when gaseous chemicals are flowed over the surface of the wafer, creating a thin film on the surface of the wafer. And as you can see, through this method, it actually will fill in any divots or changes in heights since you're flowing a gas on top of it. Um, you'll get a nice uniform layer of whatever you're depositing onto it. It's actually a pretty common form of actually depositing an oxide layer sometimes. If you want more control over it, it's a beneficial way to deposit an oxide layer. And also mention here, you can also deposit silicon nitride to act as an insulator between the gate and the silicon. Um, and it can also be effectively made to use integrated circuits, which are more practical than in lower volt applications. Physical vapor deposition sputtering. This is essentially where a plasma is used to break down a sample of metal, which then and these ionized particles can then um, move onto the wafer and are sprayed towards the wafer and deposited onto our wafer. And so here, like in the NRF, we were actually working on trying to modify our one of our old metal deposition machines to also do sputtering. Um, but we just haven't gotten around to it because last year we were gonna work on it, ran out of time. We were planning on doing it this past summer, but then COVID hit. Um, so that's probably still a project that we're working on. Currently, we're just using what's called this one evaporative deposition, but it's useful for compound coatings. Basically, what you all that you need to do it is obviously have the plasma in order to ionize the particles, the target particles that you are going to eventually deposit onto your substrate. But then you also need to put on or in DC you can put an electric field through through here, and it will attract your metal to the substrate, and it will use that electric field to essentially direct the wanted particles into the substrate. And then you have non-conductive sputtering. Um, and it just truly depends on whether or not the compound that is your target substrate is conductive. And so finally, the last one that we're going to talk about is physical vapor deposition, which is evaporative vapor deposition. And so this uses electrical resistance to heat a sample in a vacuum. So the biggest difference between chemical vapor deposition and physical vapor deposition is that generally speaking, physical vapor deposition needs to be done at a low vacuum. Um, Chemical vapor deposition can also be done at low vacuum, but it is possible to be done at uh, atmospheric pressure. Um, However, it is obviously much more expensive, and it can also be done at low pressures for cheaper. Um, but particularly with physical vapor deposition, they are always done at very, very, very low pressures. When we're working in the lab, we're typically trying to deposit our metals at around 10 to the -6 to 10 to the -7 torr. Um, so this form of vapor deposition, physical vapor deposition, uses electrical resistance to heat a sample in the vacuum. So over here you can see this is a tungsten filament between two nodes, and it's passing a current through it. You gradually increase it up. I think usually you'd get up to around 160 amps going through this. So essentially, when you think of a incandescent light bulb with the old tungsten filaments in it, as you pass a current through that, it is generating a lot of light, but it's also producing a lot of heat. And this method works through the same thought process that as you pass a current through it, it's going to be producing light, but it's also going to be producing a lot of heat just due to the electrical resistance. Um, and so since it's in a extremely low vacuum, the um, vaporization temperature of the metal becomes much, much lower. So it will actually um, turn into a liquid and then eventually a gas, which will then rise uh, through the vacuum chamber and deposit itself on our wafers, which are hung vertically above the filament down here. And so usually when we're doing this, we'll be monitoring the thickness, and we'll usually be on a matter of angstroms. Um, I'm trying to think of how many angstroms we actually would do. I think it was roughly, I want to say 50, but I can't guarantee that, considering it's been a year and a half since I've been in the lab. But you would basically just slowly and incrementally increase the current going through that filament until eventually all of the metal was vaporized. And usually you would choose a specific mass. The metal samples that you put in there to evaporate and use as your target metal would be measured out and massed out. Um, and you would have to do the math out basically to approximate how thick you want it, because the idea would just to be evaporate off all of your metal to get the ideal thickness that you wanted. Um, so the amount of let's say you were depositing aluminum, the amount of aluminum that you would want to actually have deposited would be calculated, and you would essentially use these little beads of aluminum to try to get the exact as close to the exact amount as you want as possible. And from there, I've finished. Does anyone else have any questions? Anyone?
I have one, but it's not about. I understood the material you were talking about, though.
Oh, yeah, that's good. What is your question about?
So I'm driving currently. Can I email you after this with the Professional Society participation assignment
Oh
for
yeah,
EELC?
yeah, of course.
Okay.
Yeah, whenever you have the opportunity, go ahead and send that to me.
Okay. Thank you so much.
No
Have a good
problem.
day.
Yeah, what's up, Hunter? I have the same thing. By any chance, do you have your email?
Yeah, here I'll post it in chat. It's longhunter@ufl.edu, but I'll just post it in chat just in case. Um, any other questions about the material or the Arduino project next week?
So do we just show up for next week if we're interested in the Arduino?
Have you signed up using the Excel sheet that has been posted in the group me a couple times?
No, I just joined the group meet today. You
Okay.
said it's in the group meet?
Yeah, you might need to scroll up a little bit. Give me a second. Uh, let me see if I can find the Excel sheet, and I'll just post in the chat. So
Okay.
essentially, we're doing this little Arduino project right now, and or we're in the planning process of it right now. One of our sponsors for the club wanted to. Is this your first meeting, or have you been to one of our meetings before?
Yeah, this is my first meeting.
Okay. So one of our sponsors actually wanted what they had recommended to us was we've done Arduino projects before, but they had recommended to us to actually do a um, a project that looked more into using Arduino to record data of a process of some kind and then export it so that we can actually analyze that data somehow. Um, and so obviously we didn't want to put people who had never really had experience with Arduino working on big machinery or anything like that. So we're basically what the concept is that we're going to have people build an Arduino circuit that basically analyzes whatever you want about the process of making a cup of coffee using a coffee maker. There's no extra cost to you guys. It's going to be all on us. So if you're interested, just feel free. I sent the link to the Excel sheet in chat.
Yeah, I see
So
it.
all that you need to do is just fill that out, and then next week we're gonna try to have that meeting to talk about the budget so that we can see what components you guys are gonna need for your circuits, and then we'll put it in order, and then we can actually start next semester.
All right, bet. It's gonna be the same time, right? 5 p.m.
Yes, Monday at 5.
All right. All right. Thank you, Hunter.
No problem.